Our peculiar place in the universe. It's a question that has haunted humanity for centuries. Where do we fit in the grand scheme of things? Are we special, or just another insignificant speck of dust? Let's get cosmic. We're about to embark on a journey that will challenge your perceptions of reality. Picture your home, your city, the familiar streets and buildings that define your everyday life. Now zoom out past the Earth, leaving behind the continents, the oceans, and the atmosphere that sustains us. The sun, our life-giving star, a mere speck in the vast cosmic ocean. And the Milky Way, our galactic home, a swirling island of hundreds of billions of stars. For centuries, we've believed we're just a pale blue dot in a vast, uniform universe, governed by the same laws and principles everywhere. But what if our cosmic neighborhood is actually special? What if the universe isn't as uniform as we thought? Not the center, of course, but maybe a giant cosmic pothole, a region of space that's significantly less dense than the average. This isn't just wild speculation, a fanciful idea dreamt up in the middle of the night. It's a real idea some astronomers are exploring based on actual observations and data. Why? What has led them to consider such a radical possibility? Because the universe seems to be expanding faster, here and now, than it should be according to our current understanding of cosmology. When we look far away, back in time, we get one expansion speed, a value consistent with the early universe. Locally, in our cosmic backyard, it's faster. The universe is expanding at a rate that doesn't quite match up with what we expect. This isn't a minor error, a slight discrepancy that can be easily explained away. It's a major disagreement that challenges our understanding of the cosmos, forcing us to question the very foundations of our cosmological models. So, is our model wrong, fundamentally flawed in some way? Or is our location fooling us, giving us a distorted view of the universe? Imagine standing in a less crowded patch at a concert, a small pocket of relative emptiness amidst a sea of people. The people at the edge seem to move away faster, not because they're actually moving faster, but because you're in a less dense area. Maybe the Milky Way sits inside a vast, relatively empty bubble, a cosmic void, a region of space with significantly fewer galaxies and matter than the surrounding areas. Let's explore this mind-bending possibility, this intriguing and potentially revolutionary idea. We'll look at the evidence, the observations and data that have led scientists to consider this possibility, the controversies, the debates and disagreements within the scientific community, and what it means to question our place in the universe, to challenge our assumptions about the cosmos. Are we just another speck, an average galaxy in an average location? Or are we in a special, underdense pocket of space, a cosmic void that's influencing our observations? The answer could change everything we know about the universe's history and fate, potentially rewriting our understanding of the cosmos from the Big Bang to the present day. For a scientist, there's nothing more exciting than a good mystery, a puzzle that challenges our intellect and pushes the boundaries of human knowledge. Let's get started and delve into this cosmic enigma. How did we get into this cosmic pickle? It's a question that has cosmologists scratching their heads and reevaluating some of our most fundamental assumptions about the universe. It all comes down to the Hubble constant, the universe's speedometer. Think of it as the cosmic gas pedal, dictating how quickly everything is flying apart. It tells us how fast the universe is expanding, and getting it right is a big deal. A precise measurement is crucial for understanding the universe's past, present, and future. For a while, we thought we had it figured out. We had a model, observations seemed to align, and there was a general sense of confidence. But we have two ways to measure it, and they give different answers. It's like using two different rulers to measure the same object and getting drastically different results. This is the Hubble tension, a fundamental disagreement that's shaking the foundations of cosmology. Method 1. Look at the early universe, the cosmic microwave background, or CMB. This afterglow of the Big Bang is like a baby picture of the cosmos. This predicts today's expansion rate, about 67 kilometers per second per megaparsec. Method 2. Look at the local universe, using standard candles like Type Ia supernovae. These exploding stars act as cosmic mile markers, allowing us to measure distances across vast stretches of space. This gives about 73 kilometers per second per megaparsec. 67 and 73 might not sound far apart, but in cosmology, it's a crisis. This seemingly small discrepancy has huge implications. The error bars are tiny. The two values are statistically incompatible. The level of precision in these measurements leaves very little room for error. They can't both be right if our understanding of the universe is correct. Something has to give. This Hubble tension tells us something is fundamentally wrong. There's a crack in the foundation of our cosmological understanding. Either our measurements are flawed, perhaps there's some systematic error we haven't accounted for, or our standard model of cosmology is missing something. Perhaps there's some new physics at play that we're not yet aware of. The stakes are high. The age, size, and fate of the universe hang in the balance. Our entire understanding of the cosmos is on the line. So what's going on? What could be causing this discrepancy? Is it our tools, our theory, or our place in the cosmos? Are we missing something fundamental about the universe itself? That's the mystery we're here to unravel. Join us as we delve into the heart of the Hubble tension and explore the possible solutions to this cosmic puzzle. Let's break it down with an analogy to really understand the core of the issue. Imagine measuring the height of a towering skyscraper. It's a complex task, requiring precision and accuracy. One friend, Cosmo, meticulously studies the blueprints to predict the height, 670 feet, a precise calculation based on detailed plans. Another friend, Hubble, prefers a more hands-on approach and uses a tape measure, 730 feet. A different result, obtained through direct measurement. The problem is, the building can't simultaneously be both heights. There's a discrepancy that needs resolving. That's essentially what the Hubble tension is in cosmology. It's a difference in measurements that shouldn't exist. If Cosmo is right, then maybe Hubble's tape measure is off, giving an inaccurate reading. Maybe our standard candles, the tools we use to measure cosmic distances, aren't so standard after all. If Hubble is right, then maybe Cosmo's blueprints are incomplete, missing crucial information. Maybe something fundamental about the universe changed after the Big Bang, altering the expansion rate. This isn't just a minor disagreement or a slight variation. It's a fundamental contradiction that challenges our understanding of the cosmos. The standard model of cosmology has been incredibly successful, explaining so much about the universe, but this tension is like a significant crack in its very foundation, threatening the entire structure. It forces us to question everything we thought we knew about the universe. Are our tools broken and giving us false readings, or is the underlying story of the universe itself wrong? That's why cosmologists are losing sleep, dedicating countless hours to unraveling this mystery. The tension is pushing us to consider bold, innovative, even strange and seemingly outlandish new ideas to explain this discrepancy. Maybe the problem isn't with the building itself or the tools we're using to measure it, but with the very ground we're standing on, the fundamental assumptions we've made. Could our location in the universe, our specific vantage point, be skewing our measurements and leading to this tension? That's precisely where the void hypothesis, one of the more radical explanations, comes into play. What if both Cosmo and Hubble are right? Maybe the problem isn't the building or the tools, but the ground Hubble is standing on. Enter the void hypothesis. Our galaxy might be inside a vast, underdense region, a cosmic void. The universe is like a giant sponge-dense filaments and large empty voids. The standard model assumes the universe is uniform on the largest scales. This is the cosmological principle. But the void hypothesis challenges that. Maybe we live in a bubble about 1 billion light-years across, with 20% less matter than average. It's not empty, just less crowded. If we're near the center, it would make the local universe appear to expand faster. This could resolve the Hubble tension without rewriting physics. It's a perspective problem. Our unique vantage point is fooling us. An elegant, if unsettling, solution. The universe isn't misbehaving, we just have a biased view. How does living in a void make the universe look like it's expanding faster? It's all about gravity. Matter creates gravity, which slows expansion. In a void, there's less matter, so less gravitational braking. Outside the void, dense walls of galaxies pull on everything inside. Objects in the void, like our galaxy, are pulled outward toward denser regions. It's like being on a raft in calm water, surrounded by rapids. The nearby rafts seem to move away quickly. From our perspective, the local expansion looks fast, but from a distance, the average flow is slower. The void hypothesis says this is what's happening to us. Our local measurements are biased by our underdense environment. The true global expansion rate could still be 67. Both measurements are right, they're just measuring different things. Scene transition. The void idea is a neat fix. but it challenges the cosmological principle, the belief that we don't occupy a special place. The standard model assumes the universe is homogeneous and isotropic on large scales. This principle has been the foundation of modern cosmology. But if we live in a giant void, our neighborhood is fundamentally different. That would make us cosmically special, a statistical anomaly. It's like flipping a coin 1,000 times and getting heads every time. Many scientists find this hard to accept. They'd rather tweak the standard model than believe we're in such an improbable spot. The debate is fierce. A simple, coincidental explanation versus a more complex, universal law. It's a classic scientific showdown. To challenge cosmic uniformity, we need serious evidence. The evidence might be hiding in the sound of the Big Bang itself. In the early universe, pressure waves, sound waves, rippled through the hot plasma. The biggest of these is the baryon acoustic oscillation, or BAO, a fundamental note of the cosmos. This sound wave left a faint ripple in the distribution of galaxies, a standard ruler we can use to measure distances. The size of this BAO ruler depends on local matter density. In a void, the ruler appears slightly larger. If the void hypothesis is correct, we should see this effect in galaxy surveys. The BAO scale should look stretched locally compared to the distant universe. This is a testable prediction. If we find it, the void idea gains ground. If not, the standard model stands strong. Let's appreciate the two most powerful pieces of evidence for the Big Bang, the cosmic microwave background, CMB, and baryon acoustic oscillations, BAO. The CMB is the universe's baby picture, light from when the cosmos was just 380,000 years old. It's almost perfectly uniform, but tiny ripples seeded all future structure. The BAO are linked to the CMB, sound waves in the early universe that left a fossilized imprint. The BAO scale is a standard ruler, letting us map the universe's expansion history. The standard model predicts this ruler should be the same size everywhere. The void hypothesis predicts our local measurement will be distorted. Recent surveys hint at a slight tension in BAO measurements, may be consistent with a void. It's not proof yet, but it's a tantalizing clue. The next generation of surveys will put this idea to the test. So, where does this leave us? The Hubble tension is a major cosmic puzzle. The universe appears to expand faster nearby than its early history suggests. The standard model can't explain this, but the void hypothesis might. It solves the tension without new physics, just a new map of the universe. But is such a giant void plausible? Simulations say it's extremely rare. For us to be in the middle would be an extraordinary coincidence. Scientists are skeptical and the evidence is still tentative. We need more data from upcoming surveys like Euclid and the Vera Rubin Observatory. We're at a crossroads, new physics, or a new understanding of our place in the cosmos. Either way, the Hubble tension is pushing the boundaries of our knowledge. It's forcing us to question our assumptions and seek new ways to observe the universe. The cosmos is talking. We're just beginning to understand